Everybody here for Radu's talk on hidden Hyperkähler Symmetries and Gravitational Instantons.
Thank you, Radu. So, in this talk I want to discuss.
We checked it.
We did. Okay, so I have to take notes. So I want to discuss Hyperkähler manifolds and their symmetries, and in particular hidden symmetries. And while I'm doing this, I have a very practical purpose in mind. I want to be able to write down explicit metrics. And this is a game that people always play. You use symmetry to constrain a system. In physics, in geometry as well, so in this case, you use symmetry to constrain a metric. And given a sufficient amount, in some fortunate cases, if you have enough symmetries, then you can constrain the metric sufficiently so that you can write it down explicitly, or at least assign to a given class of explicit metric. So you can write down an ansatz. And the typical example, the classic example in the Hyperkähler category is the Gibbons-Hawking ansatz, where if you have a 4n-dimensional Hyperkähler manifold with an isometric toric action of rank equal to the Quaternion dimension of the space, then the metric is given by the Gibbons-Hawking ansatz. Another example would be, for instance, if you have a 4-dimensional Hyperkähler space non-singular with isometric SO3 action, then the metric is one of the three Gucci-Hansen, Taubnat, or Atiyah. Now, a Gucci-Hansen, Taubnat are a Gibbons-Hawking type, Atiyah metric is not. What is perhaps less well known is that the Atiyah metric has a hidden symmetry. So the question I'm going to address in this talk is the following: can we reproduce this paradigm for hidden symmetries? So, in other words, are hidden symmetries constraining enough so that if we have enough of them, we can write down a metric ansatz? And the answer to this is going to be positive. Alright, so this is the physics audience. Now I'm going to review quickly uses of Hyperkähler manifolds in physics. So Hyperkähler manifolds arise as target spaces of star fields in supersymmetric field theories, which can arise from brane configurations or whatever. In 1979 or something like that, Bruno Zumino found that if you have a 4-dimensional sigma model, you impose for that sigma model to have supersymmetry, then the target space is going to have a Kähler structure. Now, similarly, in 6-dimensional sigma model, if you impose it to have supersymmetry, then target space is going to have a Hyperkähler structure. I'm going to find it later. Then you can play a dimensional reduction game in 4 dimensions. N equals 2 supersymmetry implies Hyperkähler target space in 3 dimensions. N equals 2 supersymmetry implies Kähler space. N equals 4 supersymmetry implies Hyperkähler, and so on. Hyperkähler manifolds arise also as moduli spaces of solutions of gauge theoretic equations arising from the dimensional reduction of anti-self-dual Young-Mills equations. So, as instanton moduli spaces, monopole moduli spaces, spaces of solutions hitching self-duality equations already much clear, spaces of solutions of Nernst equations, and so on. The example I'm trying to get today to is this. So, Hyperkähler manifolds arise also as solutions of the vacuum Einstein equations, in which case they are called gravitational instantons because of their analogy with Young-Mills instantons, so the gravitational analogs of Young-Mills instantons, and so on. Now, formal definition. The usual Calabi, Hyperkähler manifolds were defined by Calabi. The usual definition is the holonomy definition. You have a Riemannian manifold, and you require the holonomy of the Levi-Civita connection of that manifold to be a subgroup of SPM, which is the quaternionic unitary group. In this talk, I'm going to resort to another definition. So there are many definitions you can give to Hyperkähler manifold. I'm going to resort to a definition given by Hitchin. Hyperkähler manifold is a manifold endowed with a triplet of symplectic 2 forms omega 1, omega 2, omega 3, such that if you construct from them these endomorphisms, I1, I2, I3 of the tangent bundle, they form a representation of the imaginary quaternion algebra. That means they satisfy this algebraic equation properties. And what do we mean by symplectic forms? Symplectic form is non-degenerate. That means we can invert it. And it is closed. Now, closure implies that I1, I2, I3 are integrable complex structures. And in fact, they generate, as you all know, an S2 family of integrable complex structures. That means for each point on the 2-sphere, which I drew there, with Euclidean extrinsic coordinates x1, x2, x3, radius 1, this linear combination is also an integrable complex structure. And by the way, the same thing can be said for symplectic forms. There's not only 3 of them, but a whole 2-sphere. From these from these symplectic 2 forms, you can also construct a compatible Hyperkähler metric by this formula. So in Hitchin's definition, the symplectic forms are front and center, and everything else, every other structure can be constructed from them, such as the complex structures and the metric structure. I gave an example. Now, Twistor space. So people usually try, so the philosophy of the Twistor approach, I put it in a box here, is to encode the Hyperkähler geometry of M into the complex structure of a manifold of one complex dimension higher. So it's you have to create a dictionary between the two worlds. But it's a repackaging of the Hyperkähler data. It's nothing more. You don't gain much. It's just a nice, very clever repackaging. So Twistor space is by definition from a differential geometric point of view, it's just a direct product between the Hyperkähler manifold and the sphere of complex structures. Now on this manifold you can define the sphere complex structure S2 has its own complex structure, in which case we refer to it as CP1, the complex projective line, and there's a standard isometry, isomorphic, and the isomorphism is given by, I wrote here somewhere, I can see from here, the stereographic map, right? So you can toggle from x's to zetas and so on. So out of the complex structure on S2 and the complex structures on M, you can construct a complex structure on Z. And as a complex manifold, Z is not any longer a trivial product of two complex manifolds. This complex structure encodes very non-trivial the information there. There's also a real structure induced by antipolar conjugation on S2. Antipolar conjugation, so zeta goes to -1 over zeta bar. So this is the Twistor space here. It's the direct product of M and CP1 or S2, if you prefer. And the projection here, which I denoted with pi, it's a projection from a complex manifold to another complex manifold. So it's it turns out to be a holomorphic projection. And in the Twistor picture, each fiber is a copy of the manifold, of the Hyperkähler manifold, endowed with a particular complex structure corresponding to the point on S2 on top of which we are, and also with a rotated symplectic form, which I define here. Now, you see I used omega 1, omega 2, omega 3, omega plus, omega 0, omega minus. So the connection between these two is a Euclidean basis, this is a complex spherical basis. This reality condition is satisfied. Now, the point of this is that if you combine omega 1, omega 2 with an I there, like this, omega plus is going to be holomorphic 2,0 form with respect to complex structure I3. So then you can rotate this statement, and this omega zeta is going to be holomorphic of type 2,0 with respect to I of u. So this format can actually be defined over the whole Twistor space. It's called canonical Fibonacci-Corioto twisted holomorphic 2,0 form, and so on. You can define some metric on the Twistor space, but I'm not going to talk about that. Going to come to the topic of interest to me, that is Hyperkähler symmetries. Now, the most well-known type of symmetry is 3 holomorphic symmetry, but the way I wrote here is 3 Hamiltonian, because as I said, I use Hitchin's symplectic definition. So if you define the action of a field on the symplectic forms, then the fact that every other structure, or all the other structures on the Hyperkähler manifold can be written in terms of these, this will give me the action on metric, on the complex structures, and so on. So this in particular implies that this action is holomorphic, and moreover, this definition implies that the action preserves the metric. Another action which preserves the metric is this. So if you have a vector field, the Lie action of that vector field preserves, let's say, one of the three complex structures and rotates the other two into one another. That's also a isometric action. And I can repackage this in the on the Twistor space as this. This is trivially, it's just a trivial statement of that. And this is slightly less trivial, but that's also interesting. And now I'm going beyond isometry. So I want to define the twisted versions of these symmetries. So this is what's non-trivial now. I'm going to call them trans-3-Hamiltonian and trans-rotational symmetries. And the only difference is that now I allow the vector field X to depend on the fiber holomorphically in this way. So now instead of having a single generator here, I have two j-1 generators, which are denoted xj-1, x0, and so on here. And they are related by some sort of relationship like that, so not all of them are independent. But anyway, so there's a reality condition. This is what I call, I fatten X a little bit with, so I make it dependent on fiber. Now, you may ask the question, fine, but why do you call it a symmetry? Because I can show that this does not preserve the metric. So what do we call a symmetry in the Hyperkähler category? Well, a symmetry, the philosophy is this: something is a condition is a symmetry if it gives rise to a holomorphic structure of some sort on the Twistor space. So, to give you an example, now my talk is going to focus on this only, on these types. But from these ones, to give an example, what happens if I impose this, if I have such a vector field? This is something that I'm publishing a paper soon, hopefully, on this topic. So what you have, in this case, you have this kind of condition. And on the Hyperkähler manifold, you're going to have a hyperholomorphic line bundle. And on the Twistor space, you're going to have, so because through the Attea-Wirth correspondence, you're going to have a holomorphic line bundle endowed with a meromorphic connection with pole of order J. And the residues are going to be determined by the action. So there's a very nice, beautiful story that goes on here, imposing this condition. But one thing I want to say, I'm going to treat these cases together, and I'm going to refer to the untwisted case as J equals 1. And if you see J equals 1, this is going to be just that case. So when I say J equals 1 means I mean non-twisted case. So there are homomorphic structures on a twisted space. Now I'm going to discuss only this case. And I wrote here a classic maneuver in symplectic geometry, that is Hamiltonian vector fields, so vector fields whose Lie action preserve a symplectic structure, give rise to moment maps in this manner. And this is the so-called Cartan's magic formula. I is the insertion operator, so if you insert a vector field into a form, then you, what do you call it, contract indices, right? And D hits omega, and since all the omegas are closed, this vanishes, and you have this thing closed, and that implies locally exact. Now, if I assume that the manifold is simply connected, then it is also globally defined. So this small x's are going to be globally defined, and this is some sort of generalized moment map. And if you notice that x is twisted by O2j minus 2, omega is twisted by O2, then this is going to be twisted by O2j. And the appropriate language there is fiber bundle language, but I'm not going to go there.
May I ask a question?
Yes, please. Sure.
Just so X of zeta itself was an O2j. Capital X of zeta.
Yes, O2j minus 2.
Oh, it's O2, okay, never mind.
Yeah, so that compensates these two, and then you get there, right? Exactly. That's the whole point, like you just add enough there. So it grows a little bit when you get to moment map. Now, the point I'm trying to make is that these, what I call transitory Hamiltonian symmetries, are actually hidden symmetries. What is that, a hidden symmetry? In mathematics, we have in geometry, we have a hidden symmetry when we have a killing tensor of some sort. In this case, we have a killing spinner. So suppose M has a valence 2, 0. So here I'm going to work in 4 dimensions and 2-component spinor notation, AA prime. Right? So suppose we have a killing spinner of this sort. The parenthesis means total symmetrization. X is totally symmetric in its prime indices. Then I can define a capital X in this way with an extra index there. And I can show this valence 1, 2j minus 1 killing spinner. 1 because I have a non-prime index there. So now if I look at the components, this is a totally symmetric object. This has 2j plus 1 components. I call them xm, and I assemble them into this object. Now this, I take a pair of such indices, an A and A prime, and then call them a vector index. Then this has 2j minus 1 vector-valued components, capital Xm. I assemble them into this object, and I can show, that's a bit of effort, but you can show that they satisfy precisely the moment map equation from the previous slide. So this shows that transitory Hamiltonian symmetries are the same thing as hidden symmetries, as considered by Dunajsky and Mason, for instance. So that's why I use the language hidden symmetries. Now there's a question that physics audience can always figure out the answer quickly. The question is, how do these components transform when I rotate the twistor sphere? The components of the moment map with m from minus j to j. It's very easy, right? It's according to the unitary spin j representation of rotation group. So that is given by a Wigner D matrix. This Q is the quaternion which encodes the rotation. But there's a little slight catch there. You have to normalize them with some combinatorial factor of this sort. So then I denote the normalized objects with the upper index j. So this is like a spherical tensor. The components of the generalized moment map are actually spherical tensors with respect to rotation centers, Twistor sphere, Hyperkähler complex structures. So now I come back to what I said in the beginning. So given enough symmetries, the metric is sufficient constraint for us to be able to write down explicit formulas. Now in the J cos 1, the untwisted case, that's just the Gibbons-Hawking ansatz, and I'm going to show how that arises. And for J greater or equal than 2, there are formulas which were found by Lindstrom and Rocek, and the approach is called Generalization Transform approach. This actually arrived in a supersymmetric field theoretic context under the name of n equals 2 projective superspace. So a lot of the story here actually comes from physics and superspace, and then mathematicians gave it a fancy mathematical polish. So I'm going to stay within the mathematical paradigm here, and I'm going to just quickly describe how does one obtain the generalization transform in a twistor theoretic approach. So what the main ideas are is you cover the twistor space with just 2 open patches, which project down on the twistor sphere to an Arctic and Antarctic region, overlapping Arctic and Antarctic regions. Now, on each of these 2 patches, the holomorphic 2 form, the canonical holomorphic 2 form of the twistor space, can be written in terms of complex Radu coordinates, because it's a symplectic form on each fiber. And these, one of each is always this O2J section that I talked about previously. So that generalized moment map in this approach is a Radu coordinate. Now, on the overlap, this is how mathematicians construct things. They construct locally things, and then they patch them up. On the overlap, the Radu coordinates are related by what physics call a canonical transformation. And in this case, it's a twistor space, so it's a twisting canonical transformation. Now, the important thing is the generating function of this encodes the entire geometric information of the Hyperkähler manifold. So the whole information of that Hyperkähler manifold is contained a single holomorphic function of this variable, of this generalized moment map, which is quite powerful. Now, okay, you say, fine, this is abstract, but how do we construct it in actual computations? Well, we take this function, we integrate it over zeta, and we choose an integration. We can always choose integration control which gives us a real result. And notice that this function L is going to depend on the moduli of this section. So it's going to depend on xn once you integrate over the zetas. And the result that Lindstrom and Logic showed, it basically can be translated like this. A Kähler potential with the spectral complex structure I3 corresponding to zeta equals 0 on the twistor sphere is given by some sort of generalization transform of this function. And I'm going to write down those equations, but the idea is that there's a way to go from this function to the Kähler potential. And once you know Kähler potential and the set of corresponding complex coordinates, you can compute a metric. And this was done by Lindstrom and Logic, and the thing that you find is that the metric is going to depend exclusively on the second derivatives of this function L. Just pretty powerful statement. And these second derivatives, if you pay attention to the function I wrote there, actually do not depend on which axis you choose as long as the sum of the indices is the same. So I'm going to call that HM, any one of those second derivatives.
The metric is also an O2J, and then you're expanding, you're saying what the expansion coefficients are?
No. I'm going to write down the metric explicitly. Just a second. So this one, once again.
I meant, like, what is HM?
Oh, I define. This is the definition. The second derivatives. Oh, these are derivatives, by the way. The indices are derivatives. So L derivated with respect to. So L, remember, is an integral over this thing, and this depends on the xm. So it's eventually going to be a function of x. Second derivatives, I call them h to save space and real estate on the left. And the formulas, well, they're prettified formulas because they looked up they found them, but you can put them this way. This is the metric. These are the three components in spherical, complex spherical basis of the symplectic forms. They depend on a phi, on an A, which are given here as ratios of Hankel, determinants of Hankel matrices. What's a Hankel matrix? Well, there's Toeplitz matrices and there's Hankel matrices. Toeplitz determinants are striped like this. Hankel matrices are striped like this. On a line, the entries are the same. So as you see, the determinants depend exclusively on HM. Now, U and C are complex holomorphic coordinates with respect to I3, complex structure I3. And if you count carefully what kind of ages enter there, you can find the ones with n from 1 minus 2j to 2j minus 2. And the generalized transform, the formulas are going to be like this. U and Z are given in terms of the axis by these formulas in the case j equals 1 and these formulas in the case j greater than 2. Now, this in a projective superspace approach is a Lagrangian density. The axes are the n equals 1 components of a hypermultiplet. So, for instance, the leading term is a chiral field, the second term is a linear field, and then all the intermediate ones are auxiliary fields, and so on. So what this equation means in that context is the elimination, so putting the auxiliary fields on shell. And these are the most important things, because you have obviously too many fields here. Then you have 2j plus 1, you have too many fields. Some of this is in 4 dimensions. You only need 4. You need to put all these on shell. So by putting them on shell, you can solve for them. Well, they look kind of pretty, these formulas, but there's some objections that you can bring them, some problems with them. First objection that I have is that the n it's not even symmetric here. You see, I would very much like it to run from minus j to j and then call this object a spinner. But I can't do that. I will be able to do that soon. The second objection is that, okay, we choose, out of the many holomorphic structures that we have on the Hyperkähler manifold, we choose one, and rather arbitrarily. Why that and not another one? In some problems that may be a right choice, so good choice, but in general there's no reason why you should choose one and not that. So the U and Z are complex holomorphic coordinates with respect to an arbitrary complexation, which I kind of don't like. And the third objection, the most important objection, is that these equations are actually, especially in the case J, so in the twisted case, are actually notoriously difficult to solve. Yeah? explicitly. And this is where the field got stuck because of the difficulty of solving for these equations explicitly for a really long time. There wasn't any progress. So in the G equals, so let's do the G equals 1 case, learn from it some lessons, and then move on to G equals G greater equal than 2, so the twisted case. In the G equals 1 case, symmetry comes to the rescue. So then I can change coordinates from U to Z to a symmetry adaptive coordinate. Now, in J equals 1, I have two J plus 1 component x's. So those are going to be for J equals 1, there's going to be 3 components. Now I can write them either in spherical coordinates or in Euclidean basis. In Euclidean basis, they are x1, x2, x3, they are real. So I can assemble them into a real R3 vector. And I also chip in another real coordinate. So I go from these coordinates to those coordinates. So now I use the moment map as components as coordinates. And I get the usual Gibbons-Hawking formulas by doing this. So those formulas that I wrote on the previous slide give me the usual Gibbons-Hawking formulas with U and A given as second derivatives of this function L in this way, and psi defined as the real part of this complex coordinate U. And you can show that if you write them in this way, the Higgs field U and the connection 1 form satisfy a linear differential equation. There's a Bohr-Harmonic equation, and R can be interpreted as the moment map of this vector field with respect to omega vector is basically omega 1 and omega 2, omega 3 assembled in a vector, in a 3 vector. And psi is obviously open coordinates. So this is the usual story from Gibbons-Hawking. It's nice, it's pretty, but the problem is that the beauty is a trap here because I cannot use the same method to generalize the J greater or equal than 2 case. Why? Because if I 2J plus 1 or 2J plus 1 or generalized components of generalized moment map for J equals 2, they give me 5. That's already 1 too many because the dimension of the space is 4. So I cannot use 5 coordinates to coordinatize a 4-dimensional space, and it gets worse with using J. So what do? Well, we step back a little and go back to the fundamentals, and you have to kind of forget everything you know, and you have to think like a first-year grad student who just heard of for the first time. So your advisor comes to you and says, this is the definition of Hyperkähler space. Quaternionic this, quaternionic that. 4n dimensional manifold with this quaternionic structure and so on. Write me a metric. So what's the natural thing that you think of to use as coordinates? Well, quaternionic coordinates, right? But people who know better, well, we have moment maps, we have fancy stuff, forget that. Well, actually, your first instinct should be the best instinct because, yes, you can use quaternionic coordinates so you can actually write the Gibbons-Hawking answers in quaternionic coordinates. It's just not going to be that pretty, but it's possible. So just let me show how that's done. So in Gibbons-Hawking case, so symmetry takes center stage, but the quaternionic structure is not very clear. It's a Hyperkähler manifold. There's got to be some quaternionic structure there. This is obscured, and the point that I'm trying to make in this talk is that this is not a necessity, but a choice. And it becomes a necessity when you talk about hidden symmetries, the ones with J greater or equal to 2, because there you do not possess satisfactory symmetry-based descriptions. So I'm going to step back now. I'm going to do I'm going to remind you a few things about quaternions that I'm going to need later on. So this is the quaternion algebra. Quaternions, the non-zero quaternions endowed with quaternion multiplication, they form a group. This is the left invariant Cartan-Maurer form with 4 real components. Now you can parameterize quaternions alternatively by a length, rho, and 3 Euler angles in this way. And then sigma 1, sigma 2, sigma 3 are going to be the left invariant Cartan-Maurer form 1 contra 3, sigma 0 is going to be 0 over 2 rho. And the usual things. And also another thing I'm going to need is that Wigner D matrices give a 2J plus 1 dimensional representations of the group of unit quaternions like this. And every computer scientist knows that it's actually, in competitions, it's much more efficient to work with quaternions rather than Euler angles. So I would work with quaternions, but keep in mind that the quaternion means 3 Euler angles and the length, because I need to count every so often. I need to count recently. It's going to come in handy. Now, in the next step, I want to write Gibbons-Hawking metric in Quaternion coordinates. So that's not too fancy. You just write the vector r in spherical coordinates. But the way I write it here, now remember that this transforms like a spherical tensor of a spin 1. So instead, I kind of turn that on its head, and I say, well, I'm going to use that property to parameterize the spinners. And in this case, it's a 3 vector, but because it has 3 components, and you can relate them to vector components like that again. So say I choose a reference object, and then anything that can be reached through a rotation from that object, I'll parameterize that object through the rotation parameters that it takes to get there. Right? So I choose a vector along the 3 axis. Remember, this is plus, 0, minus. So 0 is the 3 component. So I choose a vector oriented, like a row oriented along the 3 axis, and then I rotate it. And this is basically the fancy way of saying I choose spherical coordinates for the 3 vectors. Now, superficial count gives me, well, I replace three objects, x, m, with m from -1 to 1, with rho and a unique quaternion, which has 3 Euler angles. But then, so they seem to be 4. But these zeros take care of things and actually only have 2 Euler angles, which we all know in spherical coordinates you only have 2 angles showing up. So that's okay. And what you get, you can cast the metric and the symplectic forms in this form, where thetas are some 1 forms, lambda is given by this formula. It's not too bad until you go to actually express what thetas mean in terms of the other coordinates. And I say, oh well, the theta frame is weighted to the quaternion frame given by these 1 forms by 2 successive linear transformations. And I'm going to write them here. They're not particularly pretty. You just go from 2 sigmas. You see, the 3rd sigma doesn't even show up. So things take care of themselves. To the green basis, then the thetas is expressed in terms of the green basis through these formulas. So that's why people don't work with Gibbons-Hawking ansatz in Quaternion coordinates, because it's not as pretty as the other one, right? But the point I'm trying to make here is that it's possible. So this, well, I mean,
Sigmas were the left invariant forms.
I'm sorry?
Sigma 1 and sigma 2.
Oh, sigma 1 are the Euler, I'm sorry, yeah, the Cartan-Morer for SO3. So if I want to apply this way of thinking to j greater or equal than 2, I have to figure out how to write spinners in spherical coordinates, which is a very strange thing to do. But I'm going to use the same approach. I'm going to use the same property of spinners, the fact that it transforms with respect to j, spin j representation. I'm going to choose a reference object and parameterize everything that is related by rotation from that object with the Euler angles. Note that we can construct spherical invariants, so spherical scalars or rotation variants out of spinners by coupling them as spherical tensors. So there's second order invariant, third order invariant, even higher order invariant in general. But this is a Figma 3J symbol. So this is the coupling of spherical spinners. And remember what we did in the Gibbons-Hawking case. So I chose a reference vector of this sort. Now if I choose, if I compute G2 for this one, well, I'm going to get the length squared. The second invariant is going to give me trivial 0. Anything higher is going to give me trivial 0. So I don't need to bother. So we can write this in a slightly awkward way. Rho is the positive solution of the equation x squared equals G2. It's going to become relevant when I look at the G equals 2 case. Now I choose a reference spinner. This is 2j plus 1, so it has 5 components with j equals 2. I choose 2 parameters this time. So a spinner has all of a sudden 2 radii, because you need 2 radii and 3 Euler angles to get 5. So I'm going to parameterize with some parameters C1 and E3, which I'm writing this way, and this is kind of because it works. I can't say why I choose them this way. So I parameterize the reference spinner like this, And now, if we define E2 in such a way that E1 plus E2 plus E3 equals 0, and we compute this rotation invariance corresponding to this, rotation invariance means that the Q's drop out because they are rotation invariant. Then I get these formulas for G2 and G3. And this look like you can rephrase this as follows: E1, E2, E3 are solutions of the Weierstrass polynomial, cubic polynomial, with the invariants G2 and G3 as coefficients. That's why I call them G2 and G3 to connect with the Weierstrass equation. So that all of a sudden, when I'm parametrizing spinors in spherical coordinates, I give spinors a spherical parameter, I end up with the Weierstrass cubic equation in a natural way. So then fine. Well, let's see what we can do with this. Yes.
So if I about this in terms of the original O2J multiplets, you're just constructing the various SE2 invariants.
Exactly.
It's like the modulus of an O2 multiplet. Modulus everything else you develop in O4.
Exactly. Right. And then, by the way, there's higher order here, but like, again, like only these two are independent. So you have one invariant J equals to two invariants for J equals to, I don't know how many for greater J. Now, what I'm going to do now is going to write that Leeson-Rochek ansatz in these spherical coordinates. So now I'm going to go from the components, from the 5 components of the generalized moment map. I'm going to express them in spherical coordinates. So there's a quaternion there which has 3 components, 3 degrees of freedom. There's E1 plus E3, which I call minus E2, and there's E1 minus E3, which I will call rho. So I have 5 components, and I have one constraint, generalization transform constraint. So typically here people had to solve for one of them, the middle one, and then they got stuck because things got really complicated. Now here in spherical coordinates, I solve for E2. So 1, 2, 3, 4, 5 of them. Now I solve for one of them implicitly, and it's a tremendous computation. So you take those metrics, the metric and symplectic structure formulas that I have previously expressed in spherical coordinates, you put it on a computer, and it throws you this again. So the metric can be put exactly in the same form that we put the Gibbons-Hawking ansatz, but this time there's actually it's nicer. So turns out that quaternions are really the natural thing to work in when you deal with hidden symmetry. So this time the story is the other way around. Like now quaternion is nicer and symmetries are. And the theta frame, just as before, is related to quaternionic frame spanned by the Simoa symmetry, again the Cartan-Mora form for SG3, by 2 successive linear transformations. The point I'm trying to make is that, okay, I'm going to write them down, I'm going to put them there, but the point is they depend only on Hn with n from -2 to 2. So now very symmetrically, and this looks a lot like a spinor, and it is a spinor. So actually, if you work in quaternionic coordinates, you realize that you don't need to compute as many things as before, because things simplify and they look nicer. So everything's going to depend on these, but actually they're going to depend. You have to construct these, so you regard them as spherical tensors, and you construct this composite object by coupling them by means of Clebsch coordinate coefficients, and then you can write the 2 transformations that I told you about like this. From the theta basis to the green basis, I forgot to put the color green, and then from the green basis to the quaternionic basis. And these are as explicit as you can think in terms of these things. They're really algebraic. This is easy. This is no fancy implicit solving. This is just an algebraic transformation. Right? So this is basically the generalization of the Gibbons-Hawking ansatz to a twisted case with a twisted symmetry. And if you look at it, this looks a lot. It starts looking a lot like the RTA chain mesh, which is practically essentially a particular case of this. So this is kind of the main thing at this stage. So to sum up, the J equals 2 metric, J equals 2 means we have already a twisted, a hidden symmetry there, and only a hidden symmetry. It's contained in a single holomorphic function, h of x sub zeta, and so on, which this is an O4 multiplet. And to compute a metric explicitly, we have to compute an integral like this, and then compute the second derivatives with n for minus 2 to 2. And we don't have to compute all of them, because everything that has an index m is actually satisfied this kind of reality condition. And we have to solve the generalization transform constraint. But things get nicer now, because I do not have implicit dependencies. These Quaternion coordinates are very well adapted to the problem. In computing that integral, in practice, we keep bumping into an elliptic integral associated to this particular elliptic curve. So this is mu square equals, so it's a mu zeta curve, and the x's are moduli of that curve. Now, I can transform B holomorphic with B holomorphic to Möbius transformations. I can cast this into bias transform with G2 and G3, exactly the invariants that I discussed previously. And then I can look at the Jacobian variety of that curve. And what happens is this curve, the Jacobian for this curve, is actually going to have a orthogonal structure. I'm sorry. Orthogonal lattice.
Why is it always elliptic? I thought originally it was going to keep going. And so
Yeah, that's a good question, because you know, this is j equals 2k, so it goes to power 4. You see? From when m equals minus 2, this is 0, and when m equals 2, this is 4. So it's a fourth
When you go to
order curve. It's kind of the
2j, you'll have much higher.
Exactly. Yes. It will be mu to j equals to the corresponding thing there. Yes. So that's the natural thing to consider. And a period differential first kind goes like this. So eventually, all the Jacobian variety is just form. Now there's very nice structure here. I'm gonna wave my hand because I don't know how much time I have. Not much. And I want to discuss an application of this idea. So I want to apply this to gravitational instantons. Now, again, as I said, what do I need in order to describe a Hyperkähler manifold? I need to know what kind of J I have there, what kind of hidden symmetry. That's one piece of data that I need. And the other one, I need to know that function, holomorphic function, x of zeta. So there's two things I need. Now, this, so to get there, I'm going to use an approach which was used many years ago by Hitchin in the 888. So let me say exactly what I mean. But this, I'm going to use the algebraic approach to gravitational instantons. In the beginning, I define it.
Just ask real quick. So the metric you write down previously, is it Hyperkähler for any choice of the little functions h?
Yes, that's the deal about it. It's an ansatz. So whatever you put in there, it throws you a Hyperkähler metric. That's the beauty of it. You don't need to worry.
Little h?
Yeah.
The little h's were computed by
Oh,
second derivative.
you mean, yes.
Yeah,
No.
Same thing. So
Same thing, right?
Little h's or the
Are derived from the
or
gradient.
the Legendre function or the Lagrangian. So for any such function.
So it's just like people talking out of an ansatz, you don't really care to solve the metric completely because it's given there in the textbook. So in this case, it might be. So you start with this orbifold C2 modeled out by finite side of SU2, and as we know, there's a Mackay correspondence between finite side of SU2 and fine simply list Dinky diagrams. And Felix Klein figured out, I think at the end of 19th century, that you can embed these kind of things in C3 in the following way. For instance, for gamma, the cyclic subgroup of SU2, corresponding Dinky diagram of type AK. This equation in C3, so we have x, y, and z complex coordinates, cuts down a complex surface in C3 with 4 real coordinates, so it's a 4-dimensional manifold. It's not really a manifold, it's a variety because it has a singularity at x equals y equals z equals 0. It's a singularity of type AK. And you can remove that singularity through a so-called resolution, like a minimal resolution. What is a resolution? Resolution of a singularity is a kind of a non-singular model of the singularity. And the minimal resolution means that any other resolution can be broken down to this one. So it was shown that you can deform, let's say, this equation with the deformation parameter TLs. L goes to K, satisfy this constraint. The decay, you can deform it in this way, and then it gets increasingly complicated in the exceptional cases. So you have some, now you have non-singular four-dimensional manifolds here, four-dimensional varieties. And Kornheimer famously showed in 1989 that on these minimal resolutions, one can define hyperkähler metrics. And those are the asymptotic locally Euclidean gravitational instantons. Now, Kornheimer used the Hyperkähler quotient construction, which again comes from some physics ideas, and it's beautiful and everything. It gives you a really nice conceptual understanding of these issues. It has one problem. You cannot use it to write down explicit formulas for the metric. So, because the metric says, well, there's an induced Hyperkähler metric there, but it doesn't help you in writing down explicit formulas there. And Hitchin actually did find a way around it for the HET, and then later on for the DK together with the Cherokee. And I picked again those two minimal resolutions here. And the starting point of Hitchin's argument was, well, this description is holomorphic with respect to which Hyperkähler complex structure, because X, Y, Z are holomorphic coordinates, but it doesn't say which complex Hyperkähler complex structure, because they have an S2 sphere worth of time. And his answer was, well, we cannot say which, like we cannot individualize any one of them, but it's with respect to almost all of them. And to be able to include them all, you have to rephrase your answer in terms of sections of holomorphic line bundles over the Twistor space. So then Hitchin showed that X has to be, you have to think of X here as precisely the kind of object that I discussed previously as a moment map of X sub Z of a bundle O2, and in the decay case, as an X sub Z, a section of a bundle O4. So this is J equals 1, this is J equals 2. The Z and Y's are kind of a little bit of a mess. It's not so straightforward, but X's are exactly, so the notation is very accurate. It's exactly the kind of X that I considered earlier. Now, using this, and the parameters TL in both cases are just O2 sections. Those are kind of dead parameters. They just sit there to remove the singularity, but they are not coordinates. That's a very nice story here, how you handle this. I'm going to skip most of the details. I don't have time. So as I said, since we have an O2 section here, this is just a Gibbons-Hopkin ansatz. And in this case, it's J equals 2 metric ansatz, the one I wrote with hidden symmetry. So there's a hidden symmetry in type decay. But it's constraining enough for me to be able to write down a metric. And I find the H function explicitly like this. Forget the green stuff. It's not, it doesn't come out there yet. So this is the function that I get in this case, and this is the H function that I get in that case, where the x's are O4 sections, as I said. So as I said, the H function is a function of H of zeta, x of zeta, and nothing else. Now the green deformations are the asymptotic locally flat. Yes?
Originally, H was also just separately a function of zeta.
Yes, exactly, right.
Why is
Very
that
good point.
not happening?
It just doesn't come out as, it does not depend on zeta separate. Very good point. It's a nice symmetry actually. When you don't have explicit dependence on zeta, things are nice. And you're right, it just doesn't come out as a zeta dependence. So it depends on zeta only through x in this case. So these are asymptotic locally Euclidean. They give you the asymptotic locally Euclidean metric, and these deformation. This is the so-called mass parameter in asymptotic locally. They give you asymptotic locally flat. So just asymptotic locally flat is just an extra shift of some sort. You see this x squared, but x is an O2. And this is just an x, but x is an O4. So it's we can scale this.
What are the higher multiples?
That's a very good question. So the question is like, can you repeat this for exceptional cases?
Well,
that's
my
where
question is really like, why do I have infinitely many O2 and multiplets?
No, because it doesn't work. This has just the right number of coordinates to work for this kind of singularities. This is very finely tuned.
So for E?
So it's just that, okay, the statement is, metrics of type D have a hidden symmetry with J equals 2. That's the statement. And that's only that kind of hidden symmetry. Metrics of type A have a classic isometry with J equals 1, a given total type of symmetry. This is the statement I mean, in like too many words. And I can use that to compute explicitly the Hyperkähler matrix of type D, and I'm going to get something, well, it's going to take a while to explain, and I just wrote it simply. So if you, from that age, you compute the HMs, which are double, so you compute the integral, and then you take the derivative of the integral, then the HMs are going to be of this form, where AM and PM are some spherical tensors. It's nicely behaved objects, when I say spherical tensors, explicitly given in terms of everything you have in there. Some elliptic functions, some algebraic. And you also have to compute one GLT constraint, Generalization Transform constraint, which looks a lot like a quantization condition when alpha, the mass parameter, is equal to 0. A sum of things on the Jacobian variety equals a multiple, integer multiple of the period. And I looked up, and it's funny, it's just, this is basically a quantization condition for the closure of the trajectory of an elliptic billiard. So if you have an elliptic table, and you play billiard, and you send the ball around the table, what is the condition for it to trajectory to be closed? And it's exactly this type. It's just that the billiard is there's an integrable system there somewhere. Right? So, but that elliptic billiard is it's the problem with it. I cannot draw nice pictures because it's an imaginary space. Other than that, it's like this. Well, and to finish, I'll just take the simplest possible case with k equals 0, so it has to go flat, b equals 0 metric, which is the actual hinging case. The HM, just everything else drops, and you're just left with the first term. And the constraint just says that the omega there, which unfortunately I denoted the same as that, the half period of the Jacobian variety is given exactly by the mass, so it's fixed by the mass. So we're left with only one, and then the formulas, the J-equals ansatz that I wrote, give us the beautiful D0. D0 means k equals 0 with the previous formulas. It's a dihedral singularity. I'm not sure exactly what it means.
Well, I don't.
So I went too fast. I am discussing type D, K metrics.
The dihedral symmetry only has reflection and nothing else as a generator.
It has
I mean,
reflection. What do you mean? It has. So it's the symmetry of a.
Usually K is the order, right?
Yeah.
And
Well,
this
it's not
order is
the
zero.
order. No, it's not the order. The order is a QK plus 1 or 2K plus 1 or something like that. The order is a bit. So then, if you substitute these formulas in that ansatz, you're going to get the difference of the Artier-Hitchin metric, and as a bonus, you're going to get the symplectic forms in this form. But this is just the simplest possible case of all the metrics that the decay metrics that you get. I'm going to stop here because I think I read my time. And I don't have any more slides in there. So.